in the middle of the night for me, so
Yeah.
I have said no. We have to pick a different time.
So you have a presentation with you. You will share the presentation later on.
Yeah.
Okay. All right.
Sapna, I have started YouTube Live. Okay,
Okay.
because I need to, leave. I will make you host.
Fine.
Then you can make co-host to anybody.
All right.
Or you want anybody? Dr. Kuldeep, would you be able to manage the other things if I make you host?
Yeah, no problem.
Yeah, for some emergency, I have to leave now. I have a doctor's appointment right now. Yeah. So, Dr. Kuldeep Sharma, sir, आप host बन गए हो. If you want to make co-host to anyone, now you have a right. YouTube streaming is going on. It will stop only when you end the meeting. So in the end, you have to end the meeting. That's all. Okay? Everything will be taken care. No problem.
बस सर आप ज्वाइन कर लो. Good evening. Good evening, Bhupati sir.
How are you?
I'm good. I'm good. Very nice.
Very
Professor Zollman has joined. Actually, he has joined.
Oh,
Professor
very good.
Ahluwalia has also joined.
Very good. Good evening, sir. Professor
Namaskar, sir.
Ahluwalia.
Namaskar. Thank you. Welcome, Professor Zollman. I am Dr. Ahluwalia, President IAPT. I hope I was audible.
Yes, sir. You were. Now, Professor Zollman.
Yes.
Yeah, Professor Ahluwalia has already joined. He is president of IAPT, Indian Association of Physics Teacher.
Namaste. I am Dr. Ahluwalia, and welcome to this very interesting program and the lecture. Thank you very much.
Oh, you're welcome. We'll see how interesting it is in a few minutes, right?
Yeah.
We'll wait for another 2-3 minutes.
Okay.
People are still joining. संजय सर ही ज्वाइन कर गए. संजय सर नमस्कार.
पर मैम सर नमस्ते.
Waiting for Professor Deshmukh. Professor Deshmukh has already joined. Yes. Good evening, sir. Sir,
Welcome.
yes. Sir, please unmute yourself first. Your mic is muted.
Yes, yes. Namaste. Good evening, everyone.
Good evening. Good
Sir,
evening.
sir.
Sir, our speaker has already joined.
Yes. Yeah, we are all set.
Yes.
Good morning, Professor Zollman.
Good morning.
Wonderful to have you in this meeting this morning.
Thank you.
I had a student of mine at Kansas State University by name Vinod Kumarappan. Do you know him?
No, I don't think so. Was he in physics or?
Yes. Vinod Kumarappan.
Oh, I'm sorry. Of course I do. Yes.
All right.
It's too early in the morning. Okay. Yes, I know
know.
Vinod quite well. Yeah.
Yes.
Yeah, he's been here for a long time now.
All right. So he did his master's at the IIT Madras in India.
Okay.
I was teaching there at that time, and Vinod was a student in my class, so I remember
Oh,
him for a long time.
yeah.
Professor Aluwalia, should we start actually? People will keep on joining.
Yeah, please, we should start. Yes.
We should start. Okay, so yeah, so I will start with the proceeding now. Good morning, good afternoon, and good evening to all of you. It's my great pleasure to welcome you all to this special lecture series for celebrating International Year of Quantum Science and Technology, a global tribute to one of the most profound scientific revolutions in history. This year marks a century since the foundational breakthroughs that gave birth to quantum mechanics, a theory that has transformed not just physics, but the way we understand nature at its most fundamental level. From the development of transistors and lasers to quantum computing and secure communication, quantum mechanics continues to shape the technologies of today and tomorrow. This lecture series is a part of special national events being held around the country on quantum mechanics, organized by Indian Association of Physics Teachers, bringing together researchers, educators, students, and enthusiasts to share knowledge, celebrate achievements, and inspire the next generation of quantum scientists. Since its founding in 1984, IIPT has consistently promoted a strong and dynamic community of physics educators ranging from secondary schools to institutions of higher learning. Through its workshop, conferences, publications, and outreach efforts, IIPT has remained committed to enriching the professional lives of teachers and shaping the future of physics education in India. Thank you for joining us in this exciting journey. I am delighted to extend a warm welcome to our distinguished guests and participants. First, I would like to extend a heartfelt welcome to our National President of IIPT, Professor P.K. Aluwalia, whose leadership continues to guide and inspire the community of physics educators throughout the country. I would also like to warmly welcome the Secretary of IIPT, Mrs. Rekha Ghorpade, whose continued efforts and organizational leadership have made initiatives like this possible. A very special welcome to our esteemed speaker of today, Professor Dean Zollman from Kansas State University, USA. Professor Dean Zollman is internationally renowned not only for his research, but also for his pioneering work in physics education, particularly in quantum mechanics, particularly in making quantum mechanics more accessible and meaningful for students. Professor, we are truly honored by your presence and look forward to your insights. I would also like to warmly welcome Professor P.C. Deshmukh, who is chairing today's session. Professor Deshmukh is known for his academic contributions and leadership in mentoring educators and researchers alike. Finally, I extend a warm welcome to all the participants from across the country who have joined us today. Your presence reflects our shared commitment to advancing physics education and engaging with the latest ideas and innovations in this field. On behalf of IAPT, once again, I welcome you all, and we look forward to an intellectually stimulating and inspiring session ahead. So before we begin the proceedings, I would like to invite the President IAPT, Professor P.K. Ahluwalia, to say a few words.
Thank you very much. A very good morning, Professor Zollman, and a very good evening to the participants from India. Welcome to this program. And I would like to tell the participants present here that Professor Zollman knows about IAPT. Professor B.N. Meera was with Professor Zollman, if I am right, in Kansas State University and worked with him. Sir, we are doing this kind of a series of monthly webinars to celebrate International Year of Quantum Mechanics. And this is the 7th such webinar in which we bring 6 best speakers in the area on the theme which we choose. And today's theme is very interesting, and I think we could not have found a better person than you to come and inaugurate this theme itself on teaching of quantum mechanics. We look forward to your lecture, and thanks for accepting our request. Thank you very much.
Thank you, sir. So before we start the session, let me give you a brief introduction of Professor Zollman. Professor Dean Zollman is a name well known in the field of physics education. He is a university distinguished professor and university teacher scholar at Kansas State University. And from 2001 to 2011, he served as HOD of physics and held the William and John Potter professorship. For over 5 decades, since 1972, Professor Zollman has dedicated his career to improving how physics is taught and learned. He has consistently pushed the boundaries of traditional education, exploring how students form mental models in physics, how they transfer knowledge across contexts, and how technology can reshape the classroom experience. His work has earned him some of the highest honors of the field. Among these are the National Science Foundation's Director's Award for Distinguished Teacher Scholars, the Carnegie Foundation's Doctoral University Professor of the Year Award, and the American Association of Physics Teachers Robert A. Millikan Medal. Professor Zollman has twice been a Fulbright Fellow in Germany. His international work, particularly in quantum physics education, has enriched our global understanding of how complex scientific ideas can be made accessible to students at all levels. He has co-authored educational resources ranging from video discs to textbooks and has led several influential projects. His commitment to reaching all kinds of learners, science majors, non-science students, future teachers, and more is a reflection of his belief in the power of education to inspire curiosity and change lives. We are fortunate today to learn from a scientist, a mentor, and a visionary educator. Please join me in giving a warm welcome to Professor Dean Zollman. And we are truly excited to hear from him. So before I hand over the mic to Professor Deshmukh for chairing this session, it's my great pleasure and honor to introduce Professor Deshmukhji. He's a renowned theoretical physicist whose pioneering contributions have significantly shaped our understanding of atomic and molecular processes. He has held key academic and research positions at esteemed institutions, including IIT Madras, IIT Mandi, and currently IIT Tirupati. His work spans a broad spectrum of topics in atomic and molecular physics, including light-matter interaction, ultra-fast atomic processes, and application of Lambert W function in quantum systems. He has authored over 200 research publications and several textbooks, and is also widely recognized for his commitment to science education through his NPTEL lecture series, which have reached and inspired countless students across India and beyond. Professor Deshmukh is the founder and mentor of CAMOS, the Center for Atomic, Molecular and Optical Sciences and Technologies, a collaborative initiative between IIT Tirupati and IISER Tirupati aimed at advancing frontier research and education in AMO physics. We are truly fortunate to have him with us today. Please join me in welcoming Professor P.C. Deshmukh ji. And now it's over to Professor Deshmukh ji.
Thank you. Thank you very much, Dr. Sapna. It is a great privilege, and I'm very overwhelmed by the honor of being at this session in which our speaker is Professor Dean Zollman. His contributions to physics have inspired my generation and many others, the upcoming generations as well, for so many decades. His contributions in research and in the context in which we are meeting this evening, it is his leadership in physics education. He has mentored a large number, not just of researchers, but also a large number of teachers who have learned to make physics insightful and enjoyable. I will not come in the way of the audience and Professor Zollman. May I request Professor Zollman to please initiate your talk? Thank you very much for being with us. It is a great privilege to have you this evening. Professor Zollman.
Okay. Thank you. Okay, I will share a screen. And go from there. Okay, we know I can hear you. You can hear me. I don't quite know how to get rid of this green rectangle that's on the screen.
We are able to see it clearly, Professor Zollman. There is no problem.
Okay. Okay, so let me get started. First, just let me mention that the group in physics education at Kansas State is a moderately large group by US standards. We have two faculty, one of whom is just joining us at the end of August, 3 PhD students, me, I'm the emeritus professor, and then a couple of undergraduate research students. So it's a decent sized group. Just to give you a good context, you of course are all over here, and I'm over here in the middle of the United States. So let's just get it started. And then I like to start many of my talks with this quote from Hans Christian Ørsted, who focuses on the importance of experimentation in science in general, and that all science should, in fact, start from experimentation. And that's basically the way I do my teaching as well. So I try to follow a pattern where students do something first, and then we talk about what they've done and what they've observed. Today, we're going to do something similar. We will start with a short video of an experiment, and then consider later how this experiment leads into some teaching of quantum physics, and then focus on two different ways of explaining the experiment, and in fact, much more than just the experiment. One which is very empirical, and the other is based on wave functions. So to get started, I'm going to use this little device here, which basically has a bunch of LEDs running down it. And you can see with all the LEDs on over here, and they're different colors. And as we'll see, they have some interesting properties. On the device itself, one can read the color and the wavelength, the peak wavelength for each of the LEDs. Now, whoops, let me back up. Forgot to do one thing. There. This thing is sold by a scientific company in the United States. And what it does is, in their viewpoint, is just look at the various LEDs. So I'll show you a short video of how they think it ought to be used. Okay, that's it. Now, that is rather boring, actually. And this device costs more than $100. So I don't see any reason to buy it just so you can show students different color LEDs. You can do that lots of ways. But I had a better idea. At least I thought it was a better idea. And that is, instead of just turning on each LED, connect the device to a variable power supply, and then increase the power, increase the voltage, and see what happens. So here's a schematic of what I'm doing. This took a little bit of work in that I had to do some wiring that was not quite what it was supposed to do. But here's what I'm going to show next. I'm going to show a voltage and watch the voltage increase, and then see what happens to the LED itself. And let's go ahead and do that. Now, I am going to ask you what your observations were, so be sure to pay attention. Oh, hell. Sorry about this. Okay. Okay, now I'm increasing the voltage, as you can see in the lower left-hand corner. And as I increase the voltage, you can see what happens to the LEDs on this little tower.
Mrs. Zollman, the video is not running actually.
I think so.
I'm sorry, you're not seeing it?
No.
Yeah, we are only seeing a static reading, and the
Oh.
video is not running.
Wonder why that is. Oh. Still not seeing it. No? Okay, well, I could spend probably a long time trying to figure this out, so let's not do that. When the voltage increases, what happens is at the beginning, all of these are off, and then they start coming on one at a time as the voltage goes up. So it does seem as if the color or the LED is, in fact, being turned on by a specific voltage. And I'll have to skip this because you didn't get to observe it. I'm sorry. And when we look at it and plot a graph of the wavelength of the LED versus the voltage at which it comes on, we see this kind of curve. Almost a straight line, except for this one here, and I'm going to save that one until near the end. Okay, so this type of behavior is what we would like to explain or have students explain by looking at different types of models for it. First, we're going to do the phenomenology, which means we'll say, okay, specters of LEDs are interesting, but so are gases. We'll go back to that. We'll look at energy levels, multiple atoms, multiple energy levels, and then energy bands and gaps, which of course are critical to the color of the LED. Then, and then look at the spectrum of the LEDs. We'll also take a wave function approach with a particle in a well, energy levels again, spectra will show up, multiple wave functions in multiple wells, and then again, we'll get to energy bands and gaps and the spectra of the LEDs. So we're going to do each of these in turn, doing the phenomenological one first. Now, each of these requires some background information. For the phenomenology, knowing conservation of energy, the idea that light energy comes in packets, photons, and light energy is related to color. It's about all you need to know. For the wave function one, of course, you have to know something about wave functions, standing waves, again, conservation of energy, and these last two, which are the same as the other one. Okay, phenomenological approach first is based primarily on an old project that we did called Visual Quantum Mechanics. The software and the teaching materials are still available at the website down at the bottom here. And I have all the websites in the final slide so you can look at them again and we can get them to you. Okay, now Visual Quantum Mechanics started out to be a quantum mechanics set course, not quite course, part of a course for secondary school students. Then we had advanced that into science and non-science students at the university. Quite a bit of work with present and future teachers. And then we did some more work for medical students, upper level physics students. And then we didn't intend any of this, but we have found that the web surfing public is part of what we're doing in terms of people getting involved in this. Students start with an experiment that's similar to what I just showed or tried to show, except we use much less expensive equipment. This little circuit board with an LED and a variable resistor and battery is what the students use to look at the threshold voltages of the various LEDs. And what they do observe is there is a threshold voltage. They look at the spectra of the emitted light on the LEDs and see something like this. This one is simulated, but it's the same idea. Here's what they would see in graphs, somewhat similar to what we tried to look at earlier with the LEDs. And then we have them compare them to an incandescent lamp because many of our students would have no idea what other types of light sources I don't know. I have no idea what that was. Okay, so in any case, they wouldn't know what an incandescent lamp is, so or what the light intensity looks like for that. So we have them do those as well. And just let me put these up quickly. One of the most important ones is that the colors come from clear LEDs, not just ones that have a coating on the surface. And then that the direction of the current in the LED is important to determine whether it turns on or not. So we're going to investigate these more carefully, but we start by saying, well, LEDs are a solid state device, are somewhat complicated. Let's look at gas lamps first. And what we have the students observe gas lamps, observe the lights, the spectra that comes out, and then build a model, an energy level model. And I'm going to try this. I hope it shows up.
I suspect it is running in a different window.
Okay. So you're not seeing something that says spectroscopy lab suite?
No, we can just see this slide only. We can see it on
You
Yeah.
see
slide.
only this slide.
Right.
Me,
It's running in a different window.
yeah, and I don't know
Yeah.
what
If
that
you share
window
the
might.
screen, if it will be visible to all.
Well, hell.
Needs to share the whole screen, sir.
Yes, I would think so.
No, that didn't do it.
Maybe you could stop sharing the screen and reshare it using the
Okay,
option to share the full screen.
yeah, that's what I'm trying to do now. Not having much success. It's not even. Okay, now are you seeing spectroscopy lab suite?
Yes.
Yes, okay, good. It's a little more complicated than I'd hoped for, but we'll go ahead and do this. So I pick emission spectra, and this program helps students build an energy level model of the atom. Let's put hydrogen in the power supply. And now we see on the top a spectrum of hydrogen. And my job as a student is to build an energy level model that matches that. So I add an energy level. And one energy level doesn't work. I need at least two. And then I manipulate the energy levels.
Oh, wow, this is beautiful.
God damn it.
Almost there.
Okay, finally got rid of that. Sorry about this. So in any case, so now I'm getting an energy level model, and if I add another energy level, I get, oh, very good. Now I match another one and I'm doing okay there as well. So the idea of this is that students can build an energy level model. It may not be correct by what we understand in terms of physics right now, as this one is not, but based on the knowledge that they have so far, that's all they can do. So that one works there. Now, let me go back to the slideshow. And share this screen again. Okay. So I think we're back to the slides now.
Yes.
And okay. But now with the model for the LEDs, we know the LEDs have bands of color. So since the gases have light lines, in order to make something like the LED, we must have very closely spaced energy levels. And so we would get something like this to build the energy level model of the LEDs. Then we switch to something that is closer to reality, which is energy bands and energy gaps. Within the program, the students can manipulate the width of the various bands and the distance between the bands, that is the gap, and come up with something that will match their observation of the LED spectrum. And here we see that we can do this pretty well like that and get the whole thing worked out so that the ideas of energy bands and gaps is built on basically conservation of energy from the observation of the spectra of gases and of LEDs. Okay, on to the wave function approach. Introducing the wave nature of matter is a little more difficult. Basically, what we do is say, well, let's do a double slit experiment with electrons without really being able to justify that in any real way. So we just say, let's see what happens. Okay. And our simulation of that is over here. If you're fortunate enough to have an electron diffraction apparatus, which most of us don't, excuse me, you can show the real thing, but you can show this, which is a representation of it. This thing in the middle is a Hollywood animation that is fun to watch. It's about 5 minutes long, so I'm not going to take the time to show it right now. And then there is available on the web, and I have the link at the end here, a description plus a video of something that was done just about the beginning of the 21st century at Hitachi's research facility in Japan. And you can watch a video of individual electrons reaching the screen and leaving a dot, and watch that as it starts out as just a seemingly random collection of dots, and then moving toward what we see here, which is a real interference pattern. And it's rather interesting to watch, and it is the real thing. So students can see it in that way. Of course, many students will think, well, you can do anything on video, but at least it's something that shows how things work overall. One thing that we did in our simulation is the other little guns here. The electron gun is in the power supply. But we have protons, neutrons, mesons, and photons all here. The reason that we did that was we found that students would look at the pattern and say, well, electrons have charge, therefore they're spreading out, and that's what's causing the pattern. Now, they didn't seem to connect the idea that if they just spread out, it would be a uniform distribution on the screen instead of what we see. So we put in neutrons, even though, of course, that would be very hard to do experimentally, to show that it was not a function just of the electric charge, but of something else that's going on. Now, once we have the idea that electrons do interfere with themselves, then what we need to do is introduce the idea of a wave function. We introduce the wave function and the idea of probability, and that the amplitude, and particularly the amplitude squared, is related to the probability of where the electron can be. And then we introduce the idea of a square well as a way of confining electron to a particular region. And once we have done that, then students can look at what wave functions are in various shapes of square wells. That is, they can increase this height, or they can increase the width of the well, and then they can see the various wave functions that would fit into that particular well. And we also talk about why electrons don't appear in between the two, because the wave function is not one that fits within the well, and talk about that in connection with standing waves. This particular visualization comes from the folks in Colorado, who have a number of visualizations that we use. They also have others on almost every topic in physics and some in chemistry as well. So in any case, this gets us to the idea that there are individual energy levels in a square well. We have to talk a little bit about how that well is related to what really goes on inside, say, the hydrogen atom, but that can be done as well. And here's another one where we start with the energy, the wave function, and we try to fit it into energy levels in general. This one comes from the group in Scotland at St. Andrews University that has a number of nice visualizations on quantum issues, including a little bit on quantum cryptology and quantum computing, which probably very few other people do, although your next speaker, Chandralekha Singh, has some lessons on that topic as well, but they're for more advanced students. Now, once we've got the idea of one well set up so that we know what the allowed energies are, we then move to 2 wells. And we start doing the same sorts of manipulations so that students can vary the distance between the wells. They can vary the depth and height of the wells, and the width of the wells is also. So they can start looking at those wave functions, and perhaps more importantly to where we're going in the long run, start noticing that we get 2 energy levels at each of these places, and they're rather closely spaced. And this also comes from the folks in Colorado. Then we move to multiple wells. And again, same idea, closely spaced energy levels, starting to look a little bit like energy bands and energy gaps, which of course is where we want to go with this in the long run. And now back to one of our programs, which we can put in a large number of wells and get the energy bands and gaps, and then introduce an impurity so that we get something that is more closely related to what a semiconductor is. And once we have this idea, then we can connect this one with a few energy wells to ours, which has a lot of energy wells, and then connect that back to the energy bands and gaps and the spectra that we see from the LEDs. Okay, let me pause for a second and see if there are any questions at this point.
There's no question in the chat box, and
Okay.
I think people are just listening to your talk.
Okay. Yeah. Yeah, it's always hard, and when you're doing it this way, I see a couple of faces that have their video on, but mostly I just see names, and that's not as good as being able to see people. Okay, let me talk just a little bit about the bright green LED that was the one that in this sequence, and here at least we can look at the sequence that I tried to show earlier and was not able to. You can see as they turn on, this one doesn't turn on when it should, in the sense that these things seem to be constructed so that you start at the top in terms of light, and as the voltage increases, the lights come on in order. But then we get to the third picture here, and there's one that didn't turn on, but the one after it now has. And then we go on further, and then the final one, the blue one, almost violet, turns on at the same time as that green one. Excuse me. And that's not a bad measurement. And it's not something funny about the device itself. It is, in fact, a function of what is called the bright green LED. And bright green LEDs are rather important. They are needed to make traffic lights, for example. So they do exist in nature and are needed for various things. However, it turns out that to make a bright green LED with the right bands and gaps is very expensive. And so it has not been done very well, just the same way as the other LEDs are. Instead, that green LED is in fact a blue LED with a fluorescent layer in it. And so it emits blue light, that blue light is absorbed and green light is emitted. So when you look at the graph that we looked at earlier, that green one is not on the same straight line curve as the others in this line of things. And it was actually a little bit of a mystery to me when I first did this. I couldn't understand this. I fiddled around. I finally noticed that the blue LED and the green LED came on together at the higher voltage, the 3.09 voltage. So once I got that, I already knew how white LEDs worked, and they work by fluorescence as well. I was able to figure out the rest of it. We wrote a paper on this that is listed up here, is in physics education about 5 years ago, that describes this issue. And we did it specifically because a lot of people at that time were using LEDs with their students to have their students determine Planck's constant. From that curve that I showed earlier, you have a straight line, you can figure out the slope, and from the slope, you can get Planck's constant. So it works fine, except that if they're using this green LED as one of their LEDs, then you'll get an answer that's not too good. You only get about an order of magnitude answer correct anyway, but that's why we used Planck's constant in the title of our talk, our paper. Okay, so a summary of what we've done so far is that simple experiments using LEDs can provide, just a second. Not used to talking so much so early in the morning. These can be a springboard, really, a jumping off place for activities related to quantum physics. By attempting to explain them, students can do an empirical model of atoms, energy levels in atoms and solids, and in that way learn a lot about the structure in terms of energy of atoms and materials that are solids. And likewise, we can do something that's a visual model based on wave functions. And that could be turned into a mathematical model. Now, what I have shown today are things that we don't really use the mathematics for. We're more interested in students being able to manipulate, say, the variables in a square well or the number of square wells and see how that affects the energy levels rather than having them actually do the mathematics themselves. And then they can understand anomalies like that bright green LED that don't quite fit with the model that they have so far. Okay, and let me just sort of summarize. I already have, we've seen examples of these two in what we've looked at so far. The Contemporary Physics Education Project does posters on modern topics in physics, and they do have a nice one on the applications of quantum mechanics, particularly in computing. For more advanced students, and not a lot more advanced, undergraduate level physics students, QViz, which is the group at St. Andrews University, has a very nice set of materials. Phizlets are small programs, and they have a whole set on quantum mechanics as well as things in other topics. You'll learn more at your next lecture about quilts, which is the project going forward with Dr. Singh and her group. And then another group that I haven't looked at all today is this one in Germany. It only has a few visualizations and some instructional materials doing things both in English and in German. And they're starting to work on particularly applications of quantum mechanics to contemporary engineering projects and things like that. So let me go ahead and see if this is going to show up. Okay. Are you seeing the slide or are you seeing some website?
We are seeing the website, and when you are moving the cursor, we are able to see those things popping a bit.
Okay.
With the border. Yeah.
Yeah. Okay. Great. So this gives you some idea of what the folks in Scotland have done. Oh, let me do so one thing I wanted to emphasize here is these are a little more advanced, lots of numbers and even some equations involved, but they do get into the quantum cryptography and quantum information materials, so that if you want to do that or entanglement, they have quite a bit available in that particular area. So I think it's a very good group. They make everything available for free. They have things at different levels. If we say quantum information at an introductory level, of course, we get a lot less, but we still have a lot of material that is available, and some things are Flash, so they're a little bit older, but still work fine. And some things are HTML5, so they run well in a web browser. Okay, well, at least that worked. Good. Okay, go one more level. A lot of information is available at this website called Compadre. That's run by the American Association of Physics Teachers, and it has a quantum section that is quite good. It has these Physics in it and a number of other papers as well. Physport is another thing actually also done by AAPT, which has a lot of research-based physics teaching materials, and they're not quite as well, or they're not organized in the way that you can find quantum just by adding it on as part of the website. But if you search for quantum, you'll come up with a lot of stuff. And then more recently, GREP, International Group for Physics Education Research primarily in Europe, has come up with a position paper. And the position paper is somewhat interesting, but the bibliography and webs and available materials at the end is really quite good. So it's another one where you can look at what's available and what a lot of people think have made good results out of teaching quantum mechanics. Another thing that's useful, of course, is finding out what your students really have learned. And there are 4 quantum conceptual inventories that have been published in the last many years, starting in 2002 and moving forward. I've listed them there in increasing order of use of mathematics and sophisticated quantum ideas. This one is rather sophisticated in that respect. The one I've used most is by Manjula Sharman and her group at Sydney, which is the one at the bottom of the list, and it works quite well, as do the other 2 in the middle. So these things are all available if you're trying to get a good feeling for what it is that your students have learned and how it compares to what others do as well. And I should mention all of these, if you do that, go to Physport and do a search for quantum, all 4 of these will come up and be available to you. Okay, let me just put some thanks out there for people who were involved in the visual quantum mechanics project. It was about a 10-year project overall, and we had a group of students, postdocs, visitors, one from India, Shiva Jolly, an artist, and a programmer, who I always have to say his name is Chandima Chumarangatunga, and that's so I can prove that I can say Kumarangatunga. So, and all those things are available on our website. Also available there are all of the written teaching materials that we have tested with a large number of students. The teacher's guides are not on the website because the teacher's guides contain answers to all of the questions. So if you want a copy of the teacher's guide, you've got to contact me and I can send it to you. I don't have any problems getting it out to people who have a use for it, but if I put it on the website, then students are going to start to use it. Although with AI now, I might be wasting my time trying to hide it. And so with that, I'd like to thank you. I should mention that the U.S. National Science Foundation, when it was still functioning well, supported almost all of what I've talked about here. And these are pictures of me at various times doing things I like to do. So thank you very much.
Thank you, Professor Zollman. What a fascinating talk this has been. It's a great journey. There may be some questions, so let me first invite the questions. Sapna?
Yes, sir. I am not able to see any question in a chat box, but people can unmute themselves and ask question. If anybody wants to ask any question, kindly unmute and ask the question.
Ma'am,
Yes?
can I ask my question?
Yes, sure.
Good evening, sir. My question is, if energy is quantized, what does that imply about the spectrum of light an LED can produce, sir?
I'm sorry, I didn't, what is the spectrum of light on? What was the last part of your question?
What does that imply about the spectrum of light an LED can produce, sir?
Spectrum of light that, I'm missing a word, I'm sorry.
Once again, I will repeat my question.
Yeah, Krishan Kumarji, can you explain
yeah.
it nice? Yeah.
If energy is quantized, what does
Yeah.
that imply about the spectrum of light an LED can produce, sir?
Yes. Well, each LED, the LED, if you look at just the chip inside the LED, then the spectrum of light it can produce is controlled by the bands and the gaps in the energy. So that is the way that most LEDs work, but people have gotten very clever with LEDs. So for example, a white LED that produces a complete spectrum of light and within the visible really doesn't have the band and gap that matches that. What it is a violet or ultraviolet, usually violet, LED that then puts out that violet energy. That violet energy is absorbed within the device itself, and then all colors come out of that due to fluorescence that is creating all the various colors involved. I don't know if that's answering your question or not.
Thank you, sir. Sir, I have one more question.
Okay.
How could we use LEDs to experimentally estimate speed of light or other fundamental constants, sir?
Oh, well, I mentioned using them to determine Planck's constant.
Yes.
Well, I don't know. I haven't thought about that very much. I would think, since many speed of light experiments are done with light being chopped, so you get a light pulse going out and coming back, that you should be able to do the same thing. But I don't know. I haven't thought about that.
Is it possible, sir? Is it possible to estimate the speed of light? Possible? No.
Well, the
Seems like it
energy
should
of the
be possible. Yeah.
yeah, the energy
But I
of the
haven't th-
photon
I-
is the momentum times the speed of light. So I think one could use that.
Yes.
Yeah.
Uh,
I mean, you could, yeah, okay. Oh, yes. I just thought of maybe a way to do it, which is that you don't need you need a pulse of light to measure the speed of light. So if you have an oscilloscope, it tells you when the pulse turns on and off and turns when it is turned on and off at a receiver, you should be able to get the speed of light out of that.
Thank you, sir. Thank you so much.
Sir, I've got a question, sir.
Yes.
Can you do it in this way? I may be wrong. That is, we are using this equation to find out age. Now, suppose for a particular color of light, we find out age, and for another color, we put E is equal to hc by lambda. This lambda is a measured value, E is a measured value. Now, C has been found out from another set of experiments, so we can estimate the value of see, I shouldn't say it's a determination, but it can be an estimation.
Yeah. Thank you. Okay, I'm reading a question on the chat, which asks, is a simple toy magnet an example of a macroscopic effect of quantum mechanics? Again, you're asking questions I don't quite know the answer to. I think most
Good evening,
small
Professor Zollman.
Sorry?
Yes, myself, Dr. Somnath Jalal. I have asked that question. That a magnet, a magnet can be an example of a macroscopic quantum mechanics effect, which is visible at room temperature, because generally quantum mechanics is visible at very low temperature and very small length scale.
Okay.
So is a magnet is example.
Yeah. Although I think most toy magnets are alignment of the atoms and not just the spin of the electron.
Yes, only
But
the
that's
spin degree.
but that's quantum mechanical also. Yeah. Okay. Yeah.
Yeah, because electron has both spin degree of freedom and charge degree of freedom.
Right.
The charge degree of freedom makes it a metal or insulator, and the spin degree of freedom makes it a ferromagnet or paramagnet or diamagnet.
Yeah.
So is the magnet is a macroscopic quantum effect? That is my question, sir.
Yeah. Okay. Seems to make sense. Yeah.
And sir, if you have time, may I ask a second question?
Sure.
So suppose defect in the model can be written as a non-Hermitian model Hamiltonian for any physical problem. So as for example, you showed us some example of lots of energy well, and then one of the energy well has a very deep, or maybe it has some leaky nature, so the defect.
Right.
Or for some research problem like an array of spins are sitting, and if their spin is missing, can we model the Heisenberg Hamiltonian with a non-Hermitian term? Or maybe a simple toy model of a quantum damped harmonic oscillator. How can we write the model Hamiltonian for that thing?
Ooh.
So it's a linear harmonic oscillator, but damped. The energy is decaying. How can I write the Schrodinger equation for it? Is the non-Hermitian terms should be there, or we should write the density matrix in a different way?
Right. Yeah.
I just could not stop my excitement of seeing you in front of me. That's why I said ask this question.
Yeah.
You are a role model for us.
Right. No, I'm trying to think through this. In all of our stuff, we started with some appropriate form of the Schrodinger equation, even with the periodic wells, and went from there. So underneath what the student sees on the screen is the computer's numerically solving to some point the sorting equation and putting up the wave functions and so forth.
Yeah.
But you're asking, can I go backwards, right? Can I start with that and then come up with a Hamiltonian?
Yes.
And
So suppose I'm writing the Hamiltonian for a damped harmonic oscillator, which is quantum mechanical damped harmonic oscillator.
yeah. So in principle, yes. In practice, I've never tried it.
No problem. And sir, about that macroscopic quantum thing, which is visible to all of us, can magnet be example of a macroscopic quantum event? What is your take on that thing?
Yeah.
Because I teach undergraduate student, and regularly they ask some question that, sir, how quantum mechanics is visible to us.
Okay. Yeah, you're asking really good questions that we haven't dealt with very carefully, I must say.
I request the organizer, if there is less time, I can write to Professor Zollman some other time, and you please carry on with the other question from the other
Yeah, that would be good.
That will be better.
participant.
Yeah.
Thank you, Sapna ma'am.
You can write an email to Professor Dean Zollman.
Sure.
Professor Zollman, can we share your email with him?
My name is Somnath Jalal.
Yes.
Yeah. So
I'm a physics teacher. Yeah.
So I will share the Professor Zollman's email with you, and so that you can write down your questions and get the answers from him.
Very nice, ma'am. So nice of you.
Yeah.
Thank
you. Professor Zollman, there is another question in the chat. That is by Sarmishta Sahu. She is saying, we have calculated the Planck's constant H using LEDs. The order was okay, but not the numerical value of H.
Just a second.
It is just above Somnath Jalal's question.
Oh, yeah. We've calculated, yeah. Yeah, and that's, I think, that's true. I don't know what else to say. The experiment is a little rough. First, the students have to decide exactly when that LED turns on. That's the number that you need in order to calculate H. And that's a hard thing to do. I mean, particularly if you're doing it just by eyeballing it. We have tried it with Pasco equipment, putting a what do I want to say? A photo tube right on top of the LED, turning it up and seeing when it comes on. That gives us a much better what the actual threshold voltage is. And so the more carefully you do the experiment, the better it becomes. But I think it's not perfect. It's just an experimental result that it's not the best way to calculate Planck's constant, if that's what you're aiming for.
Yes, sir. Professor Zollman, can I ask you one question? It's regarding the understanding of students. Like, how do you assess students' understanding when we use such type of visualization in a classroom?
You know, the best answer is it's a lot better than it was before they started. But it is quite different when you're trying to ascertain what students learned in this situation, say what they learned from forces and using the force concept inventory, because students don't necessarily come to a classroom with a preconceived idea about quantum physics. They're more of a blank slate, although most of them have read some things. They've mostly read that quantum mechanics is really weird, and therefore it's hard to understand, which of course is somewhat true. But overall, when we use the conceptual inventory that the folks in Sydney wrote, we find that the students do quite well on it, not as well as, of course, I would like, but do quite well once they've finished all these materials. So they do learn a lot. They learn a lot about quantized energy levels, what the word quantum even means. For most of them is something new. So they haven't done that before. So we're starting from nothing and we're making some progress, I guess is the best we can say. We have not very often found a student who has learned nothing, or even worse, a student who has gone negative compared to where he or she started. So overall, we've done a lot of research. We did, particularly at the beginning, a lot of research on high school students. Larry Escalada wrote his dissertation on evaluating things in the classroom, where he observed classrooms, he interviewed students, he interviewed teachers, and so forth, and found that there was quite a bit of learning in the whole thing.
So you mean to say pre-test and post-test will be a good idea?
Sorry?
Pre-test and post-test can be a good idea.
Yeah. And for the most part, we have not done pre-tests because we know the students don't know anything, although we have done some. We've done more pre-interviews to find out what students have, and then interviews at the end. Now, of course, that's more qualitative than actually doing a concept inventory at the beginning and the end. But yeah, all four of those inventories that I mentioned do, in fact, provide ways in which you can do pre and post testing.
Thank you.
This
Thank
is
you.
really amazing because indeed quantum mechanics is a difficult
Yeah.
subject to teach, and to make it to convey the ideas through experiential learning, showing them spectra, LEDs, and so on. I'm sure it's a great way of getting them involved. Personally, Professor Aluwalia has a question. Professor Aluwalia, please go ahead.
Thank you very much. Thank you, Professor Zollman, for a wonderful talk. You know, sometimes when we start using these resources in the classroom and talk about these to the teachers, they feel that, okay, taking all these in the classroom is quite, obscure in the sense that teachers say, okay, these resources are available, but I find that I do not get that much amount of time with the students to spend and explain all these things. And as you were showing that wave function part, where the mathematics is actually in the background in the solution of the equations, they really get put off. Would you give us your thoughts about how these things can be implemented successfully in the classroom and teachers start adopting these and adapting themselves to these resources?
Oh, very hard question. First, one thing I always try to make clear is that if we're going to add these ideas to a normal physics course, we have to remove something. You know, too many people always add one more thing to the physics course. I mean, if you look at physics textbooks, they have grown over the years until they're almost impossible to pick up because they always add one more thing. And we can't continue to do that. We have to decide what is it that we can let go of because we think it's important that students learn some issues around quantum mechanics. And that's almost has to be an individual decision, or if not an individual decision, a curricular decision for a school or a state or whoever controls those things. So that's one part of it. The other part is, you're right, what I showed today, which I did in less than an hour, would take about a month in a classroom because the students need time to interact with these things, and they always take longer than you can possibly imagine. They just do, and that's the way it is. So patience and making sure that you're giving enough time to it by removing other things from your class, your course, is about the only thing you can do. And for some teachers, that's too much. They can't do that. They've got a set that they've been using for years, and they can't see anything that's not essential from that. And if that's the case, then I think there's little room for the quantum. Sometimes we get people who decide that, but then say, well, I've got these really bright 4 or 5 students. Why don't I give them these things and get them off in the corner and let them try it and see what happens. And sometimes that works well, both from the students learning, but also that the teacher starts seeing that, hey, students can learn from this and they can even get excited about it. And so maybe it should be part of the classroom. But I think doing it slowly, doing a little bit, like maybe just the energy levels 1 year, that still would take at least a week. And seeing how that works and seeing how the students respond to it is a good way to get started. And, you know, for most teachers, when students are responding positively to something, then you try to figure out how to do it and how to do it for more students. It's not a very good answer, but I don't think there is a good answer.
But at least you have suggested one thing, which is interesting, that we should really take it in the project mode and try to do with, say, a few students and let other students hang around them. Maybe that will be a better way of doing the thing.
Yeah.
Thank you very much for that. There was a second question which I wanted to ask you is, you know, we are celebrating this 100 years of quantum mechanics. And there is a lot of, you know, fashionable thing which is being talked about now, that bring quantum mechanics in the high school, bring quantum computing to the high school. And maybe if we have to do that, again, we will have to throw away something from the syllabus and then make some space for that. Do you think that this will be a right kind of a way to this, or we should wait for the students to mature and then do it maybe at the undergraduate level and not burden unnecessarily the minds of the students in the schools with the situation where quantum mechanics becomes more weird than people think it already is?
Yeah, I've argued on both sides of this off and on, but I think that at some level, students can learn and understand certain things. And particularly what I like and what we've worked with some middle school teachers. Middle school in the United States is 6th, 7th, and 8th year, or 7th, 8th, and 9th year, depending on where you're living. But in any case, yeah, the middle part of the school is just getting students to understand the concept of building models by building the energy level of atoms. Now, that's a long way from being able to solve Schrodinger's equation, but it's a start in understanding that we can understand a lot about things that we cannot see. And we can understand these ideas because we look at the light coming out, and from the light coming out, we build backwards, and we can build a model of certain parts of the process. And I think students can learn that quite early. And I think that's important in terms of understanding how science works, not just understanding quantum mechanics, but in general how science works. And so I advocate doing it middle, 6, 7, 8, 9 grade on up to some extent, but hold back on the mathematics because it's frightening to a lot of people.
Yes.
The best part which I liked was that you brought in the Gisler tubes and you showed that energy level part. And then you went to the LEDs. And that was really very interesting that you were playing with the voltage and then different LEDs were getting lighted up. It was, a visualization of the way we see the spectrum itself, in which we are able to see distinct lines, and which is so obvious to appreciate and think of. Thank you. I think these are enough. Thank you very much for replying to my questions.
It is also remarkable that Professor Zollman has shared so many resources in this talk.
Yes, yeah.
I think I'm glad the recording of this talk, I believe, is available.
Yes, yes.
And it has enough in it for many of us to learn from for the next 2 or 3 years, I would think.
Right.
Good,
It's
good.
very rich.
I think,
Very
Mr.
rich
Deshmukh,
talk.
we should think
Yes,
of creating in IAPT the workshops on these things for
absolutely. This
the
is,
teachers and
yeah,
maybe the students also.
Yeah.
means
Yeah, and
every 2 minutes.
yeah, I did
Go
try
ahead.
to stick to freely available materials.
Yes,
There are a few that can be bought, but I think what's out there and freely available
yeah,
is
that
really
itself is
very
so
good.
much. That itself is so much and so beautiful. I mean,
Yes.
it's we are really very grateful for introducing all of us to such a wealth of knowledge. This is amazing, and it will help many of us to appreciate quantum mechanics and then to teach it to our students. So thank you very much.
Yeah,
Sapna?
there's a question in the chat about LEDs with coatings. And yeah, there are LEDs, there are red LEDs and they have red plastic around them. And I find those difficult because students equate them to other lights that have coatings around them. So we always worked hard to get clear LEDs that gave out the various colors. And that was, I think, an important part of our early development. And when we started this, it wasn't easy to find those. Most of the LEDs had a plastic coating that was the same color as the light they were emitting. But yeah, you want to stay away from that because the clear LED that puts out blue light really communicates a lot to the students.
So thank you very much, Dr. Professor Dean Zollman, for such a wonderful session. And now I would like to request Dr. Kuldeep Kumar to present finally the vote of thanks.
Thank you, Madam. Good morning, Professor Dean Zollman, and good evening to all the participants and teachers, students who have joined us today. Today, we are honored to have enjoyed a very enlightening and elaborated inaugural talk of special lecture series of this monthly webinar by Professor Dean Zollman, University Distinguished Professor Emeritus, Kansas State University, on teaching quantum mechanics and PER studies as a part of celebrating International Year of Quantum Science and Technology, IYQ 2025. Thank you very much, sir, for your very interesting talk and for demonstrating and showing how using short experiments using LEDs, we can teach quantum mechanics and visualize the fundamental concepts of wave function and energy level scheme. How do energy and wave function changes when we have two or more wells? And thank you very much, sir, for having with us today. I would also like to thank Professor P.C. Deshmukh ji, chairperson of today's session, Professor P.K. Aluwalia ji, President IAPT, and Professor Rekha Godpade Madam, General Secretary IAPT, Professor Bhupati Chakrabarti, and I would also like to thank all the participants for joining us today. I hope the participating students will definitely get benefited out of this interesting lecture. I hope we will definitely enjoy the coming lectures of this monthly webinar. And once again, I thank you all for joining us today. Thank you very much. Namaskar.
Thank you very much. And with this, we come to end of our today's session. Have a nice day, Professor Zollman, and good night, everybody. So we'll stop here.
So thank you very much and namaste
Thank you,
to all. Thank you.
sir.
Thank you, Professor. Thank you. Bye-bye. कुलदीप सर स्टॉप कर देना इसको YouTube को.
Okay.
ये जो लाइव स्ट्रीमिंग है ना इसको स्टॉप करना है.
इसमें ये लीव करने के लिए बोल रहा है, स्टॉप की ऑप्शन नहीं आ रही.
क्या बोल रहा है? लीक
लीव
लीव तो
स्टार्ट आपने किया होगा उधर से
नहीं
शायद.
नहीं उन्होंने किया था, रेखा मैम ने किया था ना, और उन्होंने बोला आपको होस्ट बनाया तो आप स्टॉप कर सकते हो.
इसमें लीव की ही ऑप्शन आ रही है.
अच्छा एक मिनट मैं देखती हूँ. तो फिर लीव कर दें. एक मिनट सर का भी कॉल आ रहा है, मैं सर से पूछ लेती हूँ. सर ये YouTube को कैसे करते हैं हम स्टॉप?
पहले एंड आ रहा था, अब नहीं आ रहा है.
तो मे बी सर हाँ ये ऐसे हो जाएगा, जब आप एंड करेंगे तो शायद अपने आप ही एंड हो जाए.
मैं
है
लीव
ना?
करूं तो हो जाएगा.
हाँ पर सर इसका एड्रेस नहीं दिया उन्होंने YouTube का, मैम रेखा ने. हम ढूंढेंगे कैसे? अच्छा ठीक है सर. कुलदीप कहाँ पे जाऊं मैं YouTube लाइव पे? अच्छा सर वहां जाना पड़ेगा. अच्छा ठीक है. अच्छा
मैं लीव कर जाऊं तो हो जाएगा.
अब अभी लीव कर देते हैं फिर हम इसको ना।
अभी लीव
हाँ
कर देंगे, खत्म
कर
नहीं
दो सर, कर दो कुलदीप सर, कर दो। ठीक, ठीक है।